A drop or droplet is a small column of liquid, bounded completely or almost completely by free surfaces. A drop may form when liquid accumulates at the lower end of a tube or other surface boundary, producing a hanging drop called a pendant drop. Drops may also be formed by the condensation of a vapor or by atomization of a larger mass of liquid. Surface tension. Liquid forms drops because the liquid exhibits surface tension. A simple way to form a drop is to allow liquid to flow slowly from the lower end of a vertical tube of small diameter. The surface tension of the liquid causes the liquid to hang from the tube, forming a pendant. When the drop exceeds a certain size, it is no longer stable and detaches itself. The falling liquid is also a drop held together by surface tension. Pendant drop test. In the pendant drop test, a drop of liquid is suspended from the end of a tube by surface tension. The force due to surface tension is proportional to the length of the boundary between the liquid and the tube, with the proportionality constant usually denoted. Since the length of this boundary is the circumference of the tube, the force due to surface tension is given by where d is the tube diameter. The mass m of the drop hanging from the end of the tube can be found by equating the force due to gravity with the component of the surface tension in the vertical direction, giving the formula where I plus or minus is the angle of contact with the tube, and g is the acceleration due to gravity. The limit of this formula, as I plus or minus goes to 90 degree, gives the maximum weight of a pendant drop for a liquid with a given surface tension. This relationship is the basis of a convenient method of measuring surface tension, commonly used in the petroleum industry. More sophisticated methods are available when the surface tension is unknown that consider the developing shape of the pendant as the drop grows. In medicine, droppers have a standardized diameter, in such a way that 1 milliliter is equivalent to 20 drops. And, for the cases when smaller amounts are necessary, microdroppers are used, in which 1 milliliter equals 60 microdrops. Drop adhesion to a solid. The drop adhesion to a solid can be divided to two categories, lateral adhesion and normal adhesion. Lateral adhesion resembles friction and refers to the force required to slide a drop on the surface, namely the force to detach the drop from its position on the surface only to translate it to another position on the surface. Normal adhesion is the adhesion required to detach a drop from the surface in the normal direction, namely the force to cause the drop to fly off from the surface. The measurement of both adhesion forms can be done with the centrifugal adhesion balance. The CAB uses a combination of centrifugal and gravitational forces to obtain any ratio of lateral and normal forces. For example, it can apply a normal force at zero lateral force for the drop to fly off away from the surface in the normal direction, or it can induce a lateral force at zero normal force. Droplet. The term droplet is a diminutive form of drop and as a guide is typically used for liquid particles of less than 500 micrometer diameter. In spray application, droplets are usually described by their perceived size, whereas the dose is a function of their volume. This increases by a cubic function relative to diameter. Thus a 50 micrometer droplet represents a dose in 65 pl and a 500 micrometer drop represents a dose in 65 nanoliters. Speed. A droplet with a diameter of 3 mm has a terminal velocity of approximately 8 meters per second. Drops smaller than 1 mm in diameter will attain 95% of their terminal velocity within 2 m. But above this size the distance to get to terminal velocity increases sharply. An example is a drop with a diameter of 2 mm that may achieve this at 5.6 m. Optics. Due to the different refractive index of water and air, refraction and reflection occur on the surfaces of raindrops, leading to rainbow formation. Sound. The major source of sound when a droplet hits a liquid surface is the resonance of excited bubbles trapped underwater. These oscillating bubbles are responsible for most liquid sounds, such as running water or splashes, as they actually consist of many drop-liquid collisions. Shape. The classic shape associated with a drop comes from the observation of a droplet clinging to a surface. The shape of a drop falling through a gas is actually more or less spherical for drops less than 2 mm in diameter. Larger drops tend to be flatter on the bottom part due to the pressure of the gas they move through. As a result, as drops get larger, a concave depression forms which leads to the eventual breakup of the drop. Size. Raindrop sizes typically range from 0.5 mm to 4 mm, with size distributions quickly decreasing past diameters larger than 2 to 2.5 mm. Scientists traditionally thought that the variation in the size of raindrops was due to collisions on the way down to the ground. In 2009, French researchers succeeded in showing that the distribution of sizes is due to the drop's interaction with air, which deforms larger drops and causes them to fragment into smaller drops, effectively limiting the largest raindrops to about 6 mm diameter. However, drops up to 10 mm are theoretically stable and could be levitated in a wind tunnel. The largest recorded raindrop was 8.8 mm in diameter, located at the base of a cumulus congestus cloud in the vicinity of Kwajalein Atoll in July 1999. A raindrop of identical size was detected over northern Brazil in September 1995. Gallery. See also, rain, pitch drop. References: Kutnell, John D. Kenneth W. Johnson. Essentials of Physics. Wiley Publishing. Roger P. Woodward, Ph.D. Surface tension measurements using the drop shape method. First 10 angstroms. Retrieved November 5, 2008. F. K. Hansen. G. Rods Run. Surface tension by Pendant drop. A fast standard instrument using computer image analysis. Colloid and Interface Science 141, 1/12 doi, 10.1016/0021-9797, 91, 90296 K. AB numerical model for the fall speed of raindrops in a waterfall simulator. October 4, 2005. Pages 2. Retrieved June 28, 2013. Prosperity, Andrea. Oghuz, Hassan N. The Impact of Drops on Liquid Surfaces and the Underwater Noise of Rain. Annual Review of Fluid Mechanics 25, 577/602. Bibcode, 1993 and RFM 25577P doi, 10.1146/ANURIVFL. 25.010193.003045. Retrieved December 9, 2006. Rankin, Ryan C. Bubble Resonance. A Physics of Bubbles, Antibubbles, and All That. Retrieved December 9, 2006. A. B. Pruacha, H. R. Pitta, R. L. A Semi-Empirical Determination of the Shape of Cloud and Raindrops. Journal of the Atmospheric Sciences 28, 86/94. Bibcode, 1971 JAT S. 28. 86P doi, 10.1175/1520-0469, 1971, 0282.0 CO. 2. Water Drop Shape. Retrieved March 8, 2008. Makvar-Kahar, Greg. Raindrop Size Distribution and Evolution. Geophysical Monograph Series 191. Bibcode, 2010 GMS. 191. 49M doi, 10.1029/2010 grams 000971. Emmanuel Villemort, Benjamin Bossa. Single Drop Fragmentation Distribution of Raindrops. Nature Physics 5, 697/702. Bibcode, 2009 NAP-PH. 5697V doi, 10.1038/NPHYS1340. Lay Summary. Hobbs, Peter V. Rangno, Arthur L. Super Large Raindrops. Geophysical Research Letters 31. Bibcode, 2004 GeoRL 3113102H doi, 10.1029/2004 gallons 020167. External links: Liquid Sculpture, Pictures of Drops, Liquid Art, Galleries of Fine Art, Droplet Photography, TVW Gallery of Drops, Pictures of Drops, Greatly Varying, Calculation of Water Waste from Dripping Tap, 1, 2, Liquid Photography, Sujhakar. This link is broken.